Hello physics students, and welcome to this video about torque. We're going to look in this video at what extended objects are, and then what torque is, and how to calculate torque. Then we're going to look at how cheater bars work. These men in this picture are using a version of a cheater bar. First, we need to identify what an extended object is. An extended object is very different from a point mass. An extended object has a definite, finite size and shape. This bowling ball, these bowling pins are extended objects. In this course, we have been treating many extended objects as point masses. And we can do that when we're describing the motion of its center of mass. But extended objects cannot be treated like a point mass when we're trying to describe rotational motion. Generally, extended objects do exhibit, or they can exhibit, both rotational and translational motion. So as we continue to look at rotational motion, we need to talk about torque, because torque is a quantity that measures the ability of a force to rotate an object around an axis. So when we talk about torque, torque depends on three things. It depends on a force, a lever arm, and the angle between the force and the lever arm. Before I go any further, I want to clarify that a force can be applied to an object without producing torque. And that occurs when no rotating motion is occurring on the object. Torque is only measuring the ability of that force to rotate the object. So if a force is being applied to an object and the object doesn't rotate, there is no torque being produced. So back to what torque depends on. There must be a force for torque to happen, and there must be a lever arm. And in this case, pretend that you're looking down on the top of a door, and this would be where the door closes, and here it is swinging open. A force is being applied to this door, and this door is moving with some angular speed in a clockwise rotation around the axis of rotation here. When we talk about the lever arm is the perpendicular distance from the axis of rotation to a line drawn along the direction of the force. So you see where the force is being applied to this door is right here at this point. So the lever arm is this distance right here between where the force is being applied and the axis of rotation, and it is perpendicular to the direction that the force is applied. So last, torque depends on the angle between the force and the lever arm, which is 90 degrees. That's just by definition that the angle between the force and the lever arm will be 90 degrees. And here is our equation for torque. We use the symbol tau, it's a Greek letter, to represent torque. Torque is equal to the force times d, which is the distance from the axis of rotation along the lever arm, times the sine of theta. We do not have to be at exactly 90 degrees in order to cause an object to rotate. We do not have to apply a force of exactly 90 degrees. You know that if you push on that door at some angle other than 90 degrees, something less than that, that you can still cause the object to rotate. However, if theta is 90 degrees, we're going to get the maximum amount of torque. Sine of theta is 1. The SI units for torque are the Newton meter. And last, we need to talk about the direction and the sign of torque. Torque is a vector quantity, and when we talk about net torque, we're going to look at the sum of all of the torque involved. So if there are multiple torques involved, we would add them up. It would look something like this. But the sign on them is very critical, and the sign represents the direction that the force is causing for the rotation. And remember, just as we've used before with our rotational motion, if the force is causing counterclockwise rotation, then the torque will be positive, and if the force is causing clockwise rotation, the torque will be a negative sign. Also, remember when you're doing your calculations to assign positive and negative values to forces and displacements as well. So let's do a sample problem together. Let's say we have a basketball and it's being pushed by 2 players during tip-off. One player exerts a downward force of 11 newtons at a distance of 7.0 centimeters from the axis of rotation. So let's draw that on our diagram. So here's our 11 newtons of force being exerted by that first basketball player, and this is the distance here, 0.07. I just converted from centimeters into meters. If we keep reading, the second player applies an upward force of 15 newtons at a perpendicular distance of 14 centimeters from the axis of rotation. So he will be applying that force at 14 centimeters from the axis of rotation over here. Now I can write down my different variables and choose the formula I'm going to use. Notice that I assigned a sign to each of these because they are vector quantities. My force 1 is in a downward direction, so it's negative, and also the distance for 2 is this far, it's a negative to the left of that axis of rotation. My net torque will be torque 1 plus torque 2, and I can find that easily using force times distance and add those together. My angle, they're perpendicular, so I don't need to worry about the sine of theta since that's 1. And I can plug values in and solve. And my net torque is equal to a negative 2.9. And the negative value is, of course, appropriate. You can see that both torques are negative, and that makes sense because each individual torque is going to cause a clockwise rotation of this basketball. And remember, the convention on that would be a negative direction. So both of them acting to cause clockwise rotation are going to definitely give us a net torque that is negative. And I just go back and check, make sure my sig figs match 2 sig figs, and that's all I can use from my problem. I'm limited to 2 sig figs. Mechanics often use what they call cheater bars to loosen very stubborn bolts. A cheater bar is typically just a length of pipe that fits over the handle of a wrench here, making that handle longer. How do they help the mechanic? Well, obviously, they increase the lever arm, but you can keep the force the same. Therefore, that increases the torque applied to this bolt. Remember, torque is equal to the force times the distance from the axis of rotation. So if you increase that lever arm and increase that distance from the axis of rotation, you can keep the force the same and apply a much greater amount of torque. Here are some advanced ideas, another advanced problem. Make up your own problems. If you have other ideas or questions, please do a little research and come in. I look forward to seeing what you have, and we'll see you in class.